Okay. Hello, everyone. The work that I'm presenting today is about a new semi-automated end-to-end encrypted cryptophone. Voice over IP is becoming one of the most dominant way of communication today. But unlike traditional telephony network, it's more susceptible to different form of attacks, including man-in-the-middle and eavesdropping attack. Actually, it's a well-known fact that governments, intelligence agencies, and cyber criminals, they often wiretap the communication for different purposes. It's either political or crime investigation. Thank you. Thank you, yeah. Or theft of sensitive information. So one essential security task is to secure, that is, to encrypt as well as to authenticate the voice over IP calls. And to do so, parties involved in the communication, they should agree on a shared key and use this key to encrypt and authenticate the communication. Preferably, this agreement should not rely on trusted third parties because they may get corrupted, or they may get compromised, or they may be under coercion of law enforcement. One relatively new class of approaches that tries to address the security of voice over IP from a purely peer-to-peer point of view is called cryptophones. The prime example is Silent Circle. You might have heard about it. Others, such as WhatsApp, Viber, Telegram, Facebook, Messenger, and Google Duo, they are also shifting towards this new form of peer-to-peer mechanism for encryption. So in this mechanism, rather than trusting on third parties, cryptophone relies on the users to authenticate the key exchange protocol. For example, here, after the key is exchanged, a SAS or short authenticated string or checksum is produced at two sides of the protocol. The devices display this to the users and ask them to compare it. Users are supposed to compare this, and the assumption is that they can compare it and they can detect the attack if these two code or checksum, they do not match. But our own studies show that human errors in this task of checksum comparison, human makes mistake, and there are human errors in this checksum comparison, and as a result, these cryptophones, unlike what they promise, they are susceptible to different form of man-in-the-middle attack, and they can be eavesdropped or wiretapped. Also, users tend to skip through the security communication, and they click through the whatever task is the security task, and they want to just go ahead and do whatever is their primary task, which is forming the call. That's why this form of communication becomes susceptible to man-in-the-middle attacks. Also, this checksum that is typically 2-word or 4-word, they promise that if it becomes longer, the security increases. But in fact, because of these human errors, it becomes more difficult for the users to compare it as it becomes longer. So the security of the protocol actually decreases with the increase in the checksum size. This is contrary to the theoretical guarantees of the protocol. Since these attacks are real, and there are several instances of man-in-the-middle attack and eavesdropping of the calls, both in the news article you can see and in the academic paper you can see that we would like to make these cryptophones robust against these type of attacks, both type of attacks that I will introduce. And also we want to have, consistent with the theoretical bound of the protocol, we want to have a system that if we increase the size of the checksum, the security of the protocol increases exponentially as the protocol promises. So in this work, we introduce cryptophone, a new model of cryptophone called CCCP. It's a new way for checksum validation model. And then this design is based on automated checksum comparison based on off-the-shelf transcription technology. We introduced this design, and we run a comprehensive usability and security study to see if we can achieve the goals that we are supposed to do. Let's look at some background of the cryptophone protocol. So the way that these protocols work is that they should agree on a key to use it in the encryption of the calls and the text messages. This key exchange, whatever the key exchange is used to produce the key, also produces a checksum. And the users are supposed to verbally communicate this checksum with each other. Like, let's say here, Alice and Bob both receive Apple Optic, and they have to verbally communicate it and compare it with what they have received locally on their device. Optionally, they should also verify each other's voice and make sure that the voice that speaks the checksum is the same voice as the person that they are going to talk to. These two tasks, checksum comparison and speaker verification, are essential to make sure that the protocol is secure. After that, if everything is fine, then every message, whether it's a file transfer or a voice call or a text message, will be secure and encrypted. The protocol guarantees that the attack will be limited, the success of the attack will be limited to 2 to the power minus k for a k-bit checksum. That means if we increase the size of the key, if we increase the size of the checksum, the attack will be less probable. Why does cryptophone require user to perform checksum comparison and speaker verification? Is because two forms of attacks against these phones. First is attack on the data channel, which is called data man in the middle. In this form of attack, the man in the middle attacker only manipulates the data communication during the protocol. And as a result, the checksum at two sides do not match. Here, one is Apple Optic, the other side is Atlas Sugar. So when they verbally exchange this checksum, and they are supposed to compare it, attack should be detected because the checksums do not match. But if the users earnestly accept the mismatching checksum, the security will be compromised. That's why the user are expected to compare the checksum. And the second attack for which the users are expected to verify the speaker is called voice man in the middle. In this form of attack, the man in the middle attack do the same thing for the data channel, but also when the users try to exchange the key verbally, they exchange the code verbally, it drops this packet and insert his or her own voice or converted or morphed voice, and then transfer the packet to the other side as expected. Here, the code again is different. One side is Apple Optic, the other one is Atlas Sugar, but when they exchange it, the attacker actually drops it, so Alice will hear someone is saying Atlas Sugar. This should be also detected, this form of attack, because the voice that speaks the checksum is not the same as the voice that they are going to talk to. But if the attacker uses some techniques, let's say voice morphing, voice synthesis, voice conversion techniques, he can convert his own or her own voice to the voice of the victim and fool the users into accepting the communication. So these two tasks, speaker verification and checksum comparison, make sure that the attacks on voice and data channel would not happen. Because of these errors that human makes in these two tasks, we see that systems are still susceptible to attacks. In our design CCCP, the main idea is to remove the human from the loop of checksum comparison. We use automated human speech transcription technology. Now that user is not successful in comparing the checksums, let's have the system compare it, and we expect the system to perform better. By doing so, we could increase robustness to data man in the middle and voice man in the middle, and we can use longer SAS or checksum because now the user is not who is supposed to compare, but the system is going to do it. So it would be more easy to use longer SAS. Our system works very similar to current cryptophone. The key exchange runs and produces two checksum at two sides. The user, similar to the current approach, verbally communicated over the voice channel that they are talking. But rather than expecting the users to compare the checksum, we transcribe it using speech-to-text transcription, and then we automatically compare it with the locally computed checksum. If the two match, there is no data man in the middle. But also, we still rely on the users to verify the speaker, so the task of speaker verification is still manual. Because we automate the checksum comparison, we improve it since the system is going to perform better than the users. And since the checksum comparison is improved, we can resist data man in the middle attack, and we have less rejections in the calls because now benign settings will not also be rejected due to human errors. That means that we have improved security and improved usability because users do not need to repeat the calls and they can just go through with the first attempt. Due to automation, the user now only needs to do one task. And it is well known that if users perform one task, do single tasking, they perform better than if they have multitask. That only task that they have to do is a speaker verification, so they perform better in the speaker verification. And the system can resist better against voice man-in-the-middle attack. Also, automation means that less burden on the users, and less burden on the users is improved usability. As I said, we can use longer checksum. Longer checksum increases the theoretical security of the protocol, which itself increases the security of the protocol. So our design is based on speech-to-text transcription. And we use the off-the-shelf speech-to-text transcription. Transcriber usually takes the voice, and based on the best matching of the words, according to the context and to the grammar model, returns a textual form of the received audio. It uses sophisticated deep learning and machine learning techniques, and it usually relies on a huge data set to get better improvement over time to recognize natural languages. Like, for example, Siri on your iPhone or OK Google, they receive your voice and then they transcribe it to text, usually based on the context that they occur to have. Like, for example, if you're texting to someone and that person is asking you, where are you? And you want to say that I'm on my way, and your voice dictating this, because they know that they can guess the context, they can better produce what you're supposed to say. But in our model, it's a bit different because checksum is 2-word or 4-word, so it doesn't have any grammar. That's why we had to fit this off-the-shelf transcription into our design. Still, the checksum comparison, automated checksum comparison, is based on speech-to-text. It starts by spotting a specific keyword, let's say go secure. When it hears go secure, it starts transcribing. It receives the audio checksum and it transcribes it and it compares it. But because the current transcription is based on the current language model, we had some errors and we had to overcome these errors. One way was to relaxing the comparison requirement. Like, for example, if the actual checksum is crucial decimal apple replica and it is transcribed as critical decimal apple replicate, here we have 2 errors, but we still accept such checksum. That means we allow the transcriber to make at least up to half of the words mistake. But of course, this will reduce the security, but we can afford it because we can have longer checksums. Also, the transcriber returns some alternative, like, for example, 8 apple. It would make sense that it is something like eat apple for the transcriber, but we have word 8 and we have word apple, and this is our checksum. In this case, transcriber may return several alternatives. We rely on 3 alternatives. If any of these alternatives are correct, we accept the checksum. If the other 2 are not valid checksums. So to understand if our system worked good or no, we ran a study. We defined 2 objectives, false positive. We defined 2 metrics, false positive rates and false negative rates. False positive rates show the instances of accepting an attack either by the transcriber or by the user. We evaluate the transcriber to see if the checksum comparison will be correct, and we evaluate users to see if the speaker verification is correct. And then we had the other 2 metrics, false negative rate of the checksum comparison and false negative rate of speaker verification, is to understand how accurate the transcriber and the user perform at the 2 tasks. Do they reject the benign cases or no? And then we also want to know that now that we are making the checksums longer, would that be more difficult, or would it take more time for the users to compare it? So we have the parameter of delay. And it all makes sense if we compare it with the traditional design, let's say Silent Circle or other traditional cryptophones, to see how well does our idea work. We set up our study. It's a web-based cryptophone. Users can connect to our phone using this website that they can just go to the website and connect to our system and then listen to some checksums that are presented to them, and then speak to our system. So it's a web-based telephony system. When they opened our website, the study website, they answered some pre-study questions. We had 66 Amazon MTurk participants in this study, and we collected over 1,600 of the samples of checksum. We asked them to call an extension on our telephony system over internet, and this kind of resembles the actual voice over IP call. So the quality that we receive here is the quality of voice over IP setup. And then we ask them to familiarize with the voice. This is important because we want to know that if they can later on be able to recognize the speaker, or if they can distinguish between two speakers, a different speaker, an attacker's voice, or the original speaker's voice. Then we ask them to speak some checksums. Later on, we're going to study the performance of checksum comparison and to see if it is able to detect the man-in-the-middle attacks and how accurate it is in the benign setting. We had 4-word and 8-word checksums here that they had to speak. And then we asked them to verify the speaker. This also represents the situation that they have to verify the speaker that they know from before or they just got familiar with. So we presented samples of original speaker that they got familiar with the voice, and then we presented samples of a totally different speaker, and we presented samples of voice converted or voice morphed samples. These converted samples are some samples that we changed the voice of the attacker such that it sounds similar to the voice of the victim using voice conversion techniques. Our transcription is, as I said, one of these off-the-shelf transcription techniques. We tested Google Speech API, IBM Watson Speech API, CMU Sphinx, and some more. And we decided to go with IBM Watson Speech to Text mainly because of the performance and the simplicity of implementation and the low error rate. So we set up this IBM Watson Speech to Text service on Watson Developer Cloud, and we send the audio files to that and receive the JSON files. And then we parse the result, the 3 alternatives, and we compared it with the corresponding displayed checksums. So now let's look at the results. The first promising result is that CCCP can effectively eliminate man-in-the-middle on data channel. So if CCCP is deployed, that means that we won't have data man-in-the-middle attack, and the security goes back to the theoretical security of the protocol. The second thing that we want to discuss is that because of the transcription error, some of the instances of benign checksum are rejected. But we go back to the relaxed mode that I said earlier, that if half of the words are transcribed incorrectly, we still accept it. In this case, the false negative rate is 4% and 7%, which is pretty low. Now let's see how well does human perform in the task of speaker verification. The first is that samples of the original speaker is presented. In this case, the false negative rate is 25% and 21% for 4-word and 8-word. Samples of a different speaker is presented. This could be the attacker who speaks the checksum. They accept it, and sometimes they may accept it, and the false positive rate is 6% and 12%, which shows instances of accepting a different voice as the original speaker. And finally, voice conversion attack, which shows that how accurate they are in recognizing a converted or synthesized voice. And it shows that 18% and 20% is the false positive rate for 4-word and 8-word. And if you look at the timing, it's about 5 seconds for the users to verify the speaker. So by increasing the size of the checksum to 8 words, it really didn't make that much difference between 4-word and 8-word. These numbers really make sense when we compare it with the current cryptophones. So let's look at one example of 4-word and 2-word and see how we improve the results. In the current design, the false positive rate of checksum comparison, that means instances of accepting a data man-in-the-middle attack, is around 30%. So if an attack happens, 1 out of 3 sessions, will still go through because of the human errors. We reduce this to 0. And this is, in fact, the most promising, and because of the presence of this type of attack in the world, there are instances that you can see everywhere. This is the most promising result. The second is that if the attacker launches a voice man-in-the-middle attack and speaks in his or her own voice, in the current cryptophone, the false positive rate is high, around 40%. We reduce this to 6%. And if the attacker presents samples of converted voice, in the current scenario, it's in the current cryptophones, we reduced it from 40% to our design to 18%. And similarly, we see that if we increase the size of the checksum from 4 word to 8 word, we still have 0% false positive rate. And similarly, false positive rate for speaker verification, for the case of different speaker and for the case of different voice, is reduced from around 40, 37, 38% to 12 and 20%. Okay, so we see that our CCCP, by automating the checksum comparison using off-the-shelf, could defeat data man in the middle, reduce the error to 0% from 30-something%. These errors often rise from human errors and click-through of the human errors. And second is that we could improve the speaker verification, possibly because now the user is only involved in one single task of speaker verification. And second is that now we are offering longer checksum. And linguistics research already show that if you present longer samples to the users, they can better verify the speaker. And finally, we can tolerate longer checksums because the system is the one that is comparing it, and thereby we offer higher theoretical security. There are still work that we need to do. One is integration with current cryptophone, let's say WhatsApp, Viber, Google, all these things, they offer end-to-end encrypted. And one is that can we integrate and how we can integrate our CCCP with these kind of voice and text messaging application. And finally, we want to improve the transcription. Our domain that the transcriber needs to work on is very limited. It's not like natural languages containing millions of sentences, possible sentences. Our domain is just, let's say, 256 or 512 words. In that case, can we improve the transcriber so that just these 500 words, transcriber transcribe it correctly? And second is that can we pick a better dictionary of the words that are better recognized by the transcriber? Like, for example, can we remove homophones, or can we pick phonetically distinct words so that it is transcribed better? I conclude my talk, and I'm happy to accept any question.
Did you consider using the other party as the transcriber? So you have Alice sees a code and says it to Bob, and he then has to type it in, because that would also reduce your errors to 0 without having to send secure information to a third party.
We did not consider this. We just automated. We are not sure if that would be easier to type it, because this is something that they have to repeat whenever a new contact is added, so that might not be very usable to ask them to type it.
Any less usable than asking them to say it?
Sorry, say that again.
But I also have another question, which is the problem with transcription software is that it's susceptible to malicious attack, particularly deep learning. And so it wouldn't be massively hard to just add perturbations to the phrase said and make the machine learning pick up a different set of words to the human ear.
So that was not our concern, because we are just using the off-the-shelf techniques like Google Cloud or IBM Cloud. That's why it was not our concern. We were not interested or concerned about designing the transcriber, but we just wanted to have something that is already built in and just rely on that.
Even though we know that the ones that are already built are weak to this kind of attack?
Yes.
Okay, thank you.
Correct. Yeah, we did not look at that.
I have a couple of questions. So the first one is, would it, because of this automated system, would it make it easier for the voice spamming? The voice, someone tries to just call.
Voice spam, you mean the voice calls?
Yeah, yeah.
So as of now, I don't know any voice spam calling on these kind of cryptophone systems.
Okay.
But one thing that you should consider is that speaker verification. So if any kind of these protocols, they require the users to verify the speaker. So if there is a spam call, that spam should be recognized by the users. So it usually makes more sense for the users who know each other or who can know each other in future conversations.
Okay. Probably the second question is related. The second one is that in your system, you're trying to reduce the cognitive burden of the users, right? Sometimes it's also like you also reduce the cognitive burden of the attacker, right? Because sometimes you can ask, because someone is calling you, the attacker is calling you, you can ask him or her to repeat the question.
If I understand correctly, is that now users is doing less things, so maybe the attacker is also using, maybe the attacker task is also less. No, the attacker should do the same thing, should manipulate the data channel and should manipulate the voice channel. Because the voice, so if we were automating the voice speaker verification, that part of the protocol, then it could be more easy. But because the still human is involved, and the attacker should still do the data man in the middle and should do the voice man in the middle, so I think it won't change the burden on the attacker.
Hi, my name is Murtuza, Wichita State University. Great talk. Just a quick question. You said you conducted a user study with 60 around participants from MacTurk. Could you comment a little bit on the generalizability of your results and what kind of demography of users?
Very good question. In our studies, we just looked at people with English as the native speaking language because the transcriber that we are using is Google. Of course, they had for different languages. They had for 88 languages, and they have for different kind of accents. But in our study, we just focused on American native speakers.
And
so, but from the aspect of which gender they are or which age or education, it's completely diverse. But all of them, they speak English as a first language.
Okay, thanks.
Thank you.